Problem number 3 deals with a triple integral. Okay, and the first question is to rewrite the integral with a different order. So the integral is given dz dy dx, and we have to rewrite the integral as dx dz dy. Okay. First of all, we have to figure out what are the bounds of x, y, and z. Okay, so z is bounded by the paraboloid and the plane z is equal to 4. So that means is above the paraboloid x squared plus y squared. So z is equal to x squared plus y squared is a paraboloid, right? And then let's say that this here is z is equal to 4. The plane z is equal to 4. So we are talking about the interior of this paraboloid. Okay, below the plane z is equal to 4, and above, so z goes from the paraboloid to the plane. Okay, y is bounded from 0 to positive square root of 4 minus x squared. So y is from 0 to square root of 4 minus x squared. That means that we are restricting this picture here, at least for now, only to values of positive y. So for now, we're dealing only with this, right? Only with this part of the paraboloid. Okay, and finally the last bound is x is between 0 and 2. So this problem, again, we're dealing with questions in the first octant, so our solid is like this. Okay, or maybe a little bit clearer picture is along the x-axis, along the y-axis. This is y, this is x, and this is z, and this is 4 right here. Okay, if we look at the shade projection onto the xy plane, we will get the circle or the quarter of the circle, this one right here, right? So this is 2 and this is also 2, so this is y is equal to square root of 4 minus x squared only in the first quadrant, if we are talking about the xy plane. Okay, so now we have to part A. I have to rewrite this integral, okay, which means that the integrand is not going to change, square root of x squared plus y squared, but it has to be dx, dz, dy. Okay, the most outside variable is y, which means right away I know that this bound is going to be y is going to be bounded by constants, so y goes from 0 to 2. Smallest value 0, largest value 2, so y goes from 0 to 2. What about x? X is bounded by, well, the smallest value of x is 0, but let's say where it goes. It goes from here, right? And the biggest value that it gets is basically the paraboloid. The formula for the paraboloid is x squared plus y squared is equal to z. X squared is equal to z minus y squared. Only x is equal to positive, because we are having only positive values of z minus y squared. So from here, x is bounded between 0 and square root of z minus y squared. Okay, so as the this integral then is nested, is the most inner integral, so z can be bounded by function of z and y, and finally z is bounded between, in order to find the bound of z, we can look only at the projection of the yz plane. If you look at only at yz plane, we have this here where z is equal to y squared, right? So z goes from y squared to 4. The ceiling is 4, and the bottom is this curve here. Y is equal to z is equal to y squared. So z is between y squared and 4. Between y squared and 4. So again, we just have to change the order of integration. We don't have to evaluate anything in this whole question. Okay. Part B is rewrite this integral in cylindrical coordinates. Okay, I'm going to take another paper here, and I'm going to sketch again what we have, okay, to have a little bit clearer idea. Okay, so this is x axis, y axis, and obviously the z axis. Okay, first of all, the integrand. The integrand is x squared, square root of x squared plus y squared, square root of x squared plus y squared. As I said in part 2 of this series of videos, you should be able to recognize x squared plus y squared as r squared. Square root of r squared is only r. Okay, which means my integral in cylindrical coordinates, right, is going to be the integrand r times, and now it's very important, don't forget the Jacobian, r dz dr d theta. Okay, now theta is very simple. Why? Because theta goes from 0 to pi over 2. So that's very simple, from 0 to pi over 2. How about r? Well, if you look at the projection of this solid onto the xy plane, what do we have? We have the circle, but only in the first quadrant, so we have only this here, and obviously r goes from 0 to 2, right? Because this was y is equal to square root of 4 minus x squared. You do the same trick like in the previous problem. Y squared is plus x squared is equal to 4, or that's 2 squared, and there you go, you have the radius is equal to 2. So r is between 0 and 2. So r is between 0 and 2. And finally z. Well, z, its lower bound is the paraboloid, and it goes all the way to 4, right? So from here all the way to 4. So z is bounded above by 4, but below z is bounded by x squared plus y squared, the equation of the paraboloid in cylindrical coordinates. That's simply equal to r squared. So z is above r squared and below 4, so from r squared to 4. So there you go. This is the integral I in cylindrical coordinates. Very, very simple, much easier way to evaluate it compared to the same integral in Cartesian coordinates. Which is not going, so this is part B, which is not going to be case for part C, so nobody would evaluate this integral in spherical coordinates, but the question is just to set it up. So let's see why it's a little bit problematic. So part C, setting up the integral square root of x squared plus y squared d what was it, dz dy dx 0 to 2, 0 to square root of 4 minus x squared, and x squared plus y squared all the way to 4 in spherical coordinates. Okay, now first of all, the easy part, square root of x squared plus y squared in spherical coordinate. Let me just remind you that x is equal to I'm blanking on what x is. Rho sine phi cosine theta. Y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Okay. In spherical coordinates, if you square both of these, right, you're gonna have rho squared sine squared phi only. Why? While x squared plus y squared is equal to rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Factor out rho squared sine squared phi. In parentheses, you have cosine squared theta plus sine squared theta, and of course this is 1, so you get rho squared sine squared phi. So x squared plus y squared in spherical coordinates is rho squared sine squared phi. Square root of that is just rho sine phi. So this integrand in spherical coordinates becomes rho sine phi. But now do not forget the Jacobian, and the Jacobian in spherical coordinates is rho squared sine squared phi d rho d phi d theta, which means this is going to result into the triple integral of rho cubed sine cubed theta d rho d phi d theta. Okay, so far so good. Nothing tricky happened here, nothing complicated happened here, but now we have to find the bounds, right? What is rho going to be bounded between? What is phi going to be bounded between? And what is theta going to be bounded between? Well, actually the last integral is the easiest one, right? We already talked that we're dealing here only in the first octant, and if we're dealing with the first octant, that means that theta goes from 0 to pi over 2. So at least that was the easy one. Theta goes from 0 to pi over 2. Where the problem arises with this particular integral? Well, look at what happens to rho. Okay, what is rho? Rho is the radius starting at 0 and going all the way to the outside boundary. Up until certain phi, the upper bound of rho is simply z is equal to 4, right? Rho goes up until here, all the way until it reaches this curve here, which is a circle, where what? Where z is equal to 4 meets the paraboloid z is equal to x squared plus y squared. And from then on, from that particular phi, rho goes from 0 to the paraboloid. Its outer boundary is the paraboloid. Okay? So something like this. And then like this. Okay, which means that rho has completely different upper bound depending on this phi, depending on this particular phi. Which means that in order to set up this triple integral, we have to split the triple integral with respect to this phi. Because when phi goes from 0 to this angle right here, and that's our job to figure out what that angle is, the boundary for theta is going to be, the boundary for rho is going to be z is equal to 4. And from this phi onward, right? The boundary for rho is going to be the paraboloid. So the main question here is, what is phi? Okay, and that's the tricky part of this question. So again, we're going to resketch this. I'm going to go very easy here explaining everything. Okay, this is the solid. Okay, and we're looking at this phi right here. So I want to know what this phi is. Okay. Well, this, as I said, you can observe this as a right angle triangle. Okay, so this plane here is z is equal to 4. That means that this length here is 4. Okay, how much is this length here? Where this length is where the paraboloid z is equal to x squared plus y squared meets the plane z is equal to 4, which means 4 is equal to x squared plus y squared, which means this is the circle with radius 2, which means that this length here is 2. Okay, pull that aside and figure out what phi is. Okay, so this is 4 and this is 2. What trigonometric function gives you is the ratio between the opposite and the adjacent. That's tangent of phi is equal to 2 over 4, or 1/2. And from here you can figure out what phi is arctangent of 1/2. Okay, so when phi is between 0 and arctangent of 1/2, the upper ceiling of rho goes from here and hits the plane z is equal to 4. Rho is between 0 and something here. So what was that upper ceiling? That upper ceiling is z is equal to 4. Well, what is z in spherical coordinates? Z in spherical coordinates is rho cosine phi is equal to 4, or only rho is equal to 4 over cosine of phi, which is 4 times secant phi. Okay? On the other hand, when phi is between arctangent of 1/2 and pi over 2, okay, the ceiling, the outside boundary of rho is the paraboloid. So rho goes from 0, right? Goes from 0 all the way to where? Where here the paraboloid z is equal to x squared plus y squared gives you the boundary. Okay, let's express this in spherical coordinates. Rho cosine phi is equal to, I already said it is very convenient to know x squared plus y squared in spherical coordinates. That's rho squared sine squared phi. We can cancel these guys out, and you have cosine of phi over sine squared phi is equal to rho. Or you can rewrite this as cosine phi over sine phi times 1 over sine phi is equal to rho. And from here, rho is equal to cotangent phi times cosecant phi, which means that when phi is between arctangent of 1/2 and pi over 2, rho is bounded between 0 and cotangent of phi, cosecant of phi. And now finally we have everything that we need in order to solve this question. So let me just remind you about the integrand in spherical coordinates, right? So I is equal to the triple integral of rho cubed sine cubed phi d rho d phi d theta. Okay, now theta, we said it's very easy. Theta goes from 0 to pi over 2 theta. Now phi, everything depended on phi. When phi is between 0 and arctangent of 1/2, between 0 and arctangent of 1/2, then a rho goes from 0 to 4 times secant phi. Rho goes from 0 to 4 times secant phi. But then plus, as we said, everything depends on phi. When phi goes from arctangent of 1/2 to pi over 2, the integrand is not going to change. Rho cubed sine cubed phi d rho d phi d theta. Again, theta doesn't change, goes from 0 to pi over 2. But now when phi is between arctangent of 1/2 and pi over 2, we calculated that rho goes from 0 to, here it is, goes from 0 to cotangent of phi, cosecant of phi. Rho goes from 0 to cotangent of phi, cosecant of phi. So this is our integral. This is this integral expressed in spherical coordinate. As you can see, it was necessary to split this integral into two triple integrals.